In this video, I want to talk to you about p-values or observed significance levels, but before I can get there, we're going to take a look back. And this might have been last week, it might have been the last lecture, whenever it happened to be for you. We were looking at an example where we were testing to determine what's the average time it takes to fill up at a gas pump. We took a nice random sample of 120 people, and we found in that sample of 120 people that the average time to fill up of the sample, the X bar value, is 4.7. We're trying to use that to determine if the average in the population, mu, is less than 5. And that's what we use these inferential procedures for. We take sample information and we try to learn about populations. Well, in order to do it, we're going to follow the classic test a hypothesis process, and that's find a test or identify the test, find the test statistic on a printout. Okay, and we see the test statistic down here, and then the classic approach says, let's take a look at a rejection region. Now, this particular problem, we used an alpha of 0.025. So because we were doing a less than test, we put the 0.025 in the lower tail of the z distribution. I'm having some trouble here with my mouse. And we found that that cutoff point is a negative 1.96. And the classic test a hypothesis technique, the rejection region technique, says we're going to reject if our test statistic falls further out there in the tail. And of course it does. It's a negative 2.191. So the conclusion we made last week or last time you were here is at this value of alpha we reject. There's sufficient evidence when we reject, there's sufficient evidence to indicate that the alternative is true, that the average time to fill up on gas at the pump is less than 5 minutes. And that's the classic test statistic, rejection region, conclusion, test hypothesis technique. And it works like a champ. However, what if I do this? What if I say, oh, did I say 0.025? I'm sorry. Let's go and use a 0.01. Well, what changes? The test doesn't change. We're still testing whether the mean's less than 5. That's still the alternative. The test statistic doesn't change, right? We still got the same sampled information. We still get the same value for the test statistic. And again, these are formulas that I don't want you to do by hand. We're going to always get those off of a printout. The rejection region changes. We now need to go and back to the table or back to the Excel function that we're using, and instead of working with the 0.025, now we're going to put in 0.01. And then what happens to this picture? Well, this line that has 0.025 beyond it that got us to the negative 1.96, it now moves to the left. It's going to slide somewhere over here where there's only 0.01, and so the negative 1.96 is going to get further out in the tail. It turns out when I do that, this new value becomes a negative 2.326. Now, the normal tables typically only go to 2 decimal places, so I found this using the norm inverse function in Excel. I put in a probability of 0.01 for a standard normal distribution, and it tells me negative 2.326. And so when I change alpha, that critical value, that rejection region critical value has got to change. And of course, now when I compare the negative 2.191 to this, it doesn't fall further out. And so now our conclusion changed. There we go. At alpha equal 0.01, we would fail to reject. Now there's insufficient evidence to indicate that the average time to fill up on gas at the pump is less than 5 minutes. And so every time I give you an alpha, I have to send you back either to a table or to the normal inverse function, so that you can get a critical value to compare the test statistic to. And it works, and it's not overly difficult. But there's another way. Because, for instance, what if I said, oh, did I say 0.01? I meant 0.02. Head back to the table. It's just, there's another way. And that's what I want to talk to you about in this video. And so the other technique is to use something called observed significance levels. Let me talk about that word significant, and I'll put the first one here. It tells us how significant our test statistic is. What does that mean? Significance or significant is a word that we use to talk about rejecting the null hypothesis. The test statistic of negative 2.191 was significant. We could reject H naught when we tested at alpha equal 0.025. It would be significant at alpha equal 0.05. It would be significant at alpha equal 0.10. As I'm raising, think about that last picture, as I'm raising the value of alpha, the cutoff point is moving closer to 0. And so if it was significant at 0.025, it's going to be significant at 0.05 and 0.10. It was not significant at 0.01. We were not able to reject H naught. So the word significance talks about our ability to reject H naught. The observed significance levels. Now, I'll talk about them today in this lecture. Typically, we call them p-values. P-values tell us how significant our test statistic is. They allow us to easily make conclusions for any choice of alpha. Now, we just saw we can make conclusions for any choice of alpha using rejection regions, but it requires a little work. We have to head back to the table. We have to head back to Excel to get a new critical value. We have to use a normal inverse function. We can do it, but it's easier when we're working with p-values. And the number one reason we love p-values, I feel like I'm giving you a top 3 list here, is that they're given to us on most computer printouts, and you can see in parentheses here, some minor modifications are sometimes needed. Typically, most software will give you p-values. Excel does a pretty good job of giving us what I want. When I've written some templates for you, or as I'm going to write templates this semester, I typically give you the p-value that you want on that template. However, there are some prepackaged analyses in Excel where we don't always get the p-value that you want. And more importantly, when you're using other software packages or when you're looking at printouts from other software packages, they don't always give you the p-value that you want. However, with some minor modifications, you'll be able to figure out the p-value pretty simply. I'm going to talk about 2 things the rest of the way in this topic. One is going to be finding p-values, and for the most part, I'm not going to ask you to do this a lot. I will probably ask you to find p-values once or twice, maybe once on a competency check, maybe once on an exam. It's important to know the process, not because you're going to have to do it very often, because again, they're given to us on most computer printouts. That's the reason we like them. But the reason I'm going to have you find p-values is once you understand how they're found, you're going to know how to do those minor modifications when needed. And so let's talk about it. The p-value is trying to tell us how significant our test statistic is. It's trying to tell us how able we are to reject H0. And what you should know, what you should understand so far is that the further that test statistic is out in the tail, the more likely we're going to be to reject H0. And the last problem was a negative 2.191, and it was significant at 0.025. What if it was a negative 3.191 or a negative 4. The further you go out in the tail, the more likely it is it's going to be beyond that rejection region cutoff. The p-value is going to try to quantify that. So what we're going to do is try to figure out how far out there in the tail is that test statistic. So we start with a sampling distribution. For right now, the only sampling distributions we've taken a look at are large sample, right? Z distributions. So we're going to be looking at the Z distribution, but we saw the T distribution earlier. When we were working with confidence intervals, it's going to make a comeback here very shortly. So draw the sampling distribution. This idea we talk about here works for T's, it works for Z's, it works for other distributions you're going to run into too. We're going to see some chi-squares and F's this semester. There are others out there. The p-value idea works for anything. So draw the sampling distribution, then put in the value to test statistic. So think about this last example. We would draw a large sample. We have a Z distribution, and we'll actually do this in a little bit. And then we're going to put in the value to test statistic. And now, how far out there is it? Well, to determine how far out there it is, we got to determine which way we're looking. We were looking to the left, so we would shade over here to the left. That's where we're going to reject. But what if it was a not equal to? Well, not equal to, what's further out there than negative 2.191? Well, negative 2.2, negative 3, negative 17. But if you're looking in both tails, you know what else is further out there? A positive 2.2 is further out there than a negative 2.191. And so in a not equal to case, we would shade both tails. We shaded the nearest tail, which in this example that we're going to look at, it would be over here. And then we would have the exact same picture in the other side. In fact, the 2-tailed p-value is going to be double the 1-tailed p-value. We'll take a look at that. So draw the sampling distribution, put in the value of the test statistic, and then shade appropriately based on the direction you're testing, and then just go find that probability. You've seen how to do this. And again, you're not going to have to do this very often. The software is going to do it for you. But you know, you can go into a norm. What would that be? If we have a test statistic, we would be going to the norm.dist function, right? And it would give us the probability. It would give us the less than or equal to probability, or the cumulative table is going to give us the less than or equal to probability, and we'd have to figure it out from there. And so that's how you find p-values. You draw in the value of the test statistic, and then you shade appropriately around it. So let's take a look at our example. Okay, in our example, we had a test statistic of negative 2.191. So I'm going to draw a normal table, or a normal picture. Let's see where my cursor is here. I've lost it. Where is it? There it is. And so the value of Z I'm going to draw in here is a negative 2.191. Because we're doing a lower tail test, I'm going to shade to the left, which is the cumulative region you see shaded in this picture. And now I'm going to go and find that. And we got a couple different ways to do that. I'm going to show you both of them here. We have the normal distribution function, and I typically use there's another one for a standard normal, but I put in a value of mu of 0, a value of sigma 1. And when I put in the test statistic negative 2.191 and put true, it gives me the cumulative probability of 0.0142. That's the probability below a negative 2.191. If I'm using the Z table, I would look up the test statistic negative 2.19, and I would have to round it to 2 decimal places, so I'd go to 2.19, and I would come down here in the lower right hand corner and you see the probability of 0.0143. You notice that I get a different value here because Excel allows me that third decimal place. But you can see I'm going to get the same or virtually the same probability regardless of which technique I use. And so that's the probability in the lower tail. Now what I'm going to tell you is that for every test statistic there's 3 possible p-values, one for each possible direction that you want to test in HA. The less than picture is right there. For a less than test, the p-value is 0.0142. What happens if I wanted to do a not equal to? This is what I was saying on the previous slide. For a not equal to, you're going to draw the sampling distribution. You're going to draw in the value of the test statistics. I'm going to put in the negative 2.191 here. And then when I go to shade appropriately, I'm going to shade to the nearest tail. And then I'm going to go over to the other side and shade the other tail. This would be the probability above a positive 2.191. And collectively, that's the probability of seeing a test statistic when you're looking in both directions that's further out than a negative 2.191. Well, we know those probabilities. The probability in the lower tail is 0.0142. The probability in the upper tail is 0.0142. And so the two-tailed probability is 0.0284. Now, what I said earlier, these values will be given to you on the printouts. There's some minor modifications that are necessary. Sometimes, depending on the software you're using, you can specify which test you want to conduct. You can say, I want to do a less than test, and you'll get the less than p-value. Or you can say, I want to do the greater, or the not equal to test, and you get the not equal to p-value. But other times, you don't get to make those choices. Some of the prepackaged analyses automatically give you a specific p-value. And a lot of times, not always, there's one time in Excel where this won't be the case, but a lot of times, if the software packages are going to give you one of the p-values, it's going to give you the two-tailed p-value. It's going to say, all right, you want to test? Here's your two-tailed p-value. Now, if you want to do a two-tailed test, that's great, use it. But what if you wanted to do this test here? What if you wanted to do the one-tailed test? That's where you got to modify it. If you see a two-tailed p-value of 0.0284, split it in half. The one-tailed p-value is half of the two-tailed p-value. Most times. There are some really weird, unusual situations where that's not true, but that's what happens most of the time. The two-tailed p-value is double the one-tailed p-value. And so you can make an easy modification when necessary. And so I wish I could tell you that the software always gives us the p-value that we want. It's just not true. And so you got to be prepared to make that modification. What's the best way to prepare? Know how p-values are found. That's why we're doing this. There is one other situation. What if we were doing the greater than test? I've already talked about the less than test, which is what we were doing in this case. The p-value for our test is in fact 0.0142, the example we were using with the gas pump times. The not equal to test is another possibility in this case. Probably unlikely is the greater than test. But maybe you're doing a greater than test. So what happens in that situation? See if I can get my cursor to go there. There we go. We put in the test statistic, a negative 2.191. All right, we still have that. Draw the sampling distribution, draw the test statistic. That's not changing. But now when we go to shade appropriately, I'm going to shade to the right. So I'm going to shade all this direction out here. When I look up that 2.191, that negative 2.191, I still see a 0.0142. That's still the probability in the lower tail. But now I don't want that probability. I want the probability in the upper tail, so I subtract it from 1. And you can see how these two p-values are always going to sum to 1. This is unusual. If you have a negative test statistic, it's rare you're doing a greater than test. Sometimes it happens. But more often than not, if you have a negative test statistic like we do here, you're either going to be doing the less than test or the not equal to test. And those are the two that I really want to highlight. If I had a greater than test, the test statistic is usually positive. But there are 3 possible p-values, and you should be able to find the p-values for each of those. More importantly, when you're looking at printouts, you just want to be on the lookout. Is the printout giving me the p-value that I want for the test that I want to conduct? If I'm doing a less than test, am I looking at a less than p-value? If so, use it. A lot of the templates I have, I've created a less than p-value, a not equal to p-value, and a greater than p-value. And then you just have to go in there and choose the correct one to interpret. Which gets us to the interpretation. And I mentioned there's 2 things to do with p-values. One is finding p-values, which I spent, 5-8 minutes talking about. And I prefaced it by saying you're not going to have to do this very often. The more important task is interpreting p-values. And again, the p-values are typically going to be given on printouts, so all you need to do is interpret them. I'm looking at my little timer right now, and I'm about 15.5 minutes. We'll be done by 20 minutes. While finding p-values is not nearly as important, it takes more time to go through and to talk about and to help you understand. Interpreting p-values is quick. How do we interpret p-values? Here it is. If p is low compared to our alpha value, you're going to reject H0. If p is low, reject the hoe. I would love to take credit for that. I really would. But I always have to give a nod to a student I had many years ago. Her name was Gabby. I had a way to interpret p-values. I thought it was the best thing since sliced bread. And I told it to the class, and the class, oh, that's good, yeah. And Gabby says, I have a better way. And I said, no, you don't, Gabby. Come on, I've been teaching for 20 years. Come on. And I said, go ahead, what do you got? She said, well, her high school AP stat teacher said, when p is low, reject the hoe. And it's kind of funny, and it always works, and it's really better than what I was teaching. And so that's what you guys are going to work with. When p-value is low, and typically I leave this part that compared to alpha out of it, when p is low, reject the null hypothesis. What about when p is high? Well, I'd love to say there's a fancy, when p is high, let the hoe fly. That doesn't work. When p is high, when p is high, don't mess with your volume. When p is high, yeah, I got nothing. When p is high, what we're going to end up with is fail to reject the null. So we got when p is low, reject the hoe. When p is high, fail to reject the null hypothesis. So how does this work? Well, quite simply, actually. The p-value in our test, we were doing a less than test. The p-value was 0.0142. Now remember the rejection region approach? We said at alpha equal 0.025. We had to go to the table. We had to get the negative 1.96. We compared it to the negative 2.191. And we're like, aha! We can make a conclusion now. With the p-value approach, just take a look. Is 0.05? Let's say we're testing at 0.05. The p is low. Reject. How about 0.025? Reject. 0.01. Now p is high. We fail to reject. It really is that simple. You give me a p-value, I can make a conclusion. What did I say earlier? It allows us to make conclusion, to easily make conclusions for any choice of alpha. That's verbatim from a couple slides ago, and it's true. What if I was testing at 0.015? P-value is low, reject. What about 0.013, which would be a really weird p or alpha to test at, by the way. But if alpha was 0.013, then the p-value is high. We would fail to reject. And so once you learn how to work with p-values, on the printout is going to be the test statistic and maybe a choice of, or one way, there's going to be a way on the printout of finding the p-value that you want. Now just compare it to the alpha you want to test with. There it is. The single most important thing I teach in this semester is right there. When p is low, reject the hoe. There's a t-shirt out there with that law on it that I don't get to wear very often because people look at me funny. Probably during an office hour for your third project. Who knows? I may be wearing my when p is low, reject the hoe t-shirt. That's how important it is. It really is going to help you make conclusions for any test hypothesis. Not just what we look at this semester, but any. And so that's going to wrap up our conversation about p-values. If and when you have questions, you know how to get hold of us. We're here to help. Good luck.